Well, happy Sabbath, everyone. Welcome to our Friday night study. I guess we can look at it as Vespers. Um, we're going to continue reading through the book, God's Celestial Clock. As I write these chapters, I've done a lot of revision, and I'm going to have to slow down a little bit as far as how much we read, but I think I need a bit more help. But anyway, before we do that, let's have a word of prayer. Dear gracious Heavenly Father, we are thankful once again that you have brought us through another week and that we have an opportunity in the Sabbath hours to have fellowship with you and with one another. So we invite your Spirit to be in our midst. And we're thankful for your answers to prayer and the way that you are working in the lives of those around us and in our own lives. And so we give our hearts to you and ask you to guide and direct every step that we take. So, Lord, as we begin to read again, I just pray that you can give guidance and direction on how best to communicate this message in this book. So we pray for your presence and we ask it in Jesus' name. Amen. Okay. So I think, last week when I read through all of this stuff, I went kind of quick. And I know that there's some things that we don't understand. I went through it and actually did a lot of revision of what I had written. And the one thing in particular is this rolling coin paradox, or where we get, I used the diagram of the rolling coin paradox to illustrate the problem that we have between the sidereal day and the sidereal month. So you'll see what I mean by that in a second once I get this shared. So I'm going to review some of these things, and it definitely doesn't hurt to review these things. Now we have this. Oh, I see that's up there. It should be here. I'm just going to make this a bit smaller. There we go. Oh, that didn't work. It's still not working. What's going on? There. I'll fix that later. Can you see that? Maybe I need to make it bigger. Okay, I'm going to make it bigger. I'm going to have to edit that. We'll go back up here and just read about this sidereal. Because this was the thing that caused Stephen so much difficulty when he was reading my other book. Okay, so the ruler of the night, the moon. Okay, so that's stealing. Is this in the right spot? Okay, I see. The witness of the stars. I guess that's where I start. If the sun governs the year and the moon governs the month, then the stars are the silent, immovable witnesses. They constitute the distant, unalterable standard against which all celestial motion is measured. And they reveal a profound mechanical truth that the glare of the sun obscures. Now, one of the things that I need to work into the book is there's many things that the ancients noticed in the sky that actually shows that the Earth is not the center of the solar system. But they didn't have, for some reason, they didn't interpret it that way that we know of. Now, it could be that some people knew that the Earth and the moon revolve around the sun. But definitely, if they did know that in the past, that knowledge had not been preserved because it is discovered in more modern times that the Earth is actually not the center of the solar system. But we're going to try, and I have to be careful as I go through this, because one is, we know there are people who are flat earthers and some who are believe in a geocentric solar system. And I'm not trying to offend anybody, but we know that they're observing certain types of things in the sky, such as retrograde movement of the planets. Plus, they also are going to notice the sidereal month. And we're going to get into that. And that's like very, very interesting. So there's a lot of things that I was doing this week in sort of researching and trying to understand certain things, how to present them. But I haven't figured out how, I haven't got them into words yet. So anyway, we have the witness of the stars. Now, part of that is when we were looking at the Song of Solomon, or Song of Songs, or Canticles, it has different titles. And I made a suggestion that the Song of Solomon, that the Shulamite is the moon, the beloved is the sun, and then the sun has his attendants, his fellows that go with him, which would be the planets, because they move with the sun through the ecliptic. And then the moon, its attendants are the stars. And mostly because we see the moon at night. Obviously, we can see the moon during the day too. And so there's a whole bunch of things that comes from looking at the Song of Solomon that way. And I really actually need to write an entire chapter dealing with the Song of Solomon. I mean, it's almost, in looking into it, I could write a commentary on the Song of Solomon that addresses the celestial references. So I think that's kind of fascinating. Now, I don't know, because I searched on the internet, there are people who notice some of the references, but I don't think that there's anybody who's ever said that the Song of Songs, or the Song of Solomon, is actually based upon the sun and moon and the stars and the planets. They'll notice things, fair as the sun, clear as the moon, awesome as an army with banners, regarding to the Shulamite, mentions, some of the constellations and things. But I think that there's a lot more to it. And I'm not sure what it means, probably in the context of our morning studies where we're addressing, the dates and the calendars and so forth from a prophetic point of view, that there might be something hidden there in the Song of Songs that has never been noticed. But that's like a huge study. That would be something we'd have to decide, to do as a group, I would think, because there's so much there. But anyway, we have the witness of the stars. So these are the attendants of the Shulamite. Now, before we can read the dial of God's clock, we must first understand the two distinct movements that govern our world, rotation and revolution. And of course, that revolution is not like political revolution. But we have a rotation of the Earth. The Earth rotates on its axis. Now, the moon also rotates on its axis, but do we see it rotating?
No, I don't think so.
Yeah, it doesn't rotate in relation to the Earth, but the ancients understood that it did rotate.
Yeah, rotate, but we can't see it.
Yeah, because the same side of the moon is always facing us, right? So we don't
Tidally locked.
Yeah, so the dark side of the moon is the side of the moon that we never saw until we sent spacecraft up to the moon and they orbited the moon. It's the first time we got pictures of the dark side of the moon. So often people use these words interchangeably in casual conversation. But when we're talking about celestial mechanics, they describe entirely different actions. So the rotation of in space, you don't rotate around the sun. We revolve around the sun and we rotate on an axis. The sun has an axis, it rotates as well. The moon rotates, and we see this with the planets. There are stars that rotate. There's one star, I can't remember its name. It's near the galactic center of the Milky Way, and it rotates. I can't remember how many times it was.
Sagittarius A or Sagittarius. All right.
What's that about Sagittarius?
Sagittarius area there.
I don't know.
They call it.
I'm not sure. But this
That's what they call it, the center area there, Sagittarius.
Sagittarius. Okay. Yeah.
Thanks.
Yeah, this one 716 times per second. It rotates. So it spins. No, they don't all spin in the same direction. Kelly
Oh,
asked this.
Venus spins opposite.
Yeah.
Venus does.
Yeah, they don't all rotate or spin in the same. So rotation is like a spinning, right? Now, a revolution is the act of traveling in an orbit around an external center point. So think of a runner running a lap around a track. For the Earth, one complete revolution around the sun gives us the measure of the year. So now when it comes to when we look at the moon and we're on Earth, we see the moon orbiting the Earth. We see the moon rising and setting, but we're not actually seeing its orbit because we're also rotating, right? So that creates a bit of confusion from a geocentric point of view, but we'll address that later. Now, the thing that I had to address was this problem of which I use the rotating coin. So the breathtaking complexity of God's calendar arises because these two movements do not happen in isolation. They are mechanically locked together. To understand how a revolution alters a rotation, consider the simple puzzle of earthly mechanics, the rolling coin. Imagine a coin with a marked face. Well, we can actually have a picture of it. If you draw a straight line on a table exactly equal to the circumference of that coin, and you roll the coin from the start of the line to the finish line, the face of the coin will turn upside down and then right side up exactly once. The coin traveled a set distance, and the result was exactly one rotation. Now imagine taking the exact same line and bending it into a perfect circle. This circle happens to be the exact size of a second identical coin. Place that second coin flat on the table and roll your marked coin completely around its edge. So if you just had another coin, you could do it with a coin like we're going to show in the picture. Your rolling coin travels the exact same distance it did on the flat line, right? Because it's the same distance. And you might logically assume it will spin exactly one time, but watch closely. By the time it completes its journey around the center coin, the marked face will have turned upside down and right side up twice. So this is the diagram. So I got Canadian quarter with King Charles on it in this diagram. Now you can see here we got there's some King Charlie, and you got panel one here. So it's upside right if you can see the head, right? And if you turn it 1/4, right, it'll then be on its side. He's looking up, and then you turn it again, you'll be looking down, right? I could have had these like closer together, but and then he's going to be looking down. So here he's going to be looking up. So he's upside down looking to the right, and now he's going to be looking down, and then he's back up again. So when that happens, it's only going to be one rotation, right?
Yeah, that's kind of
Now,
interesting.
yeah. So now we do this with a coin. So you have a coin on the table, another coin the same size, and if you rotate this moving coin, here it's facing left, just like the center one is. But if you you go 90 degrees around the orbit, you'll see it actually will turn upside down. And that's because it's not only just um, moving along the line, but it's also revolving around the other coin. It's doing an orbit, called a circular line or an orbit around it. So at 90 degrees orbit, it's going to be upside down. And then when you go 180, it will actually be upside right again. Then you go now to 270 degrees of its orbit, it'll be upside down. And then you complete, and that should be 360. I'm going to change that. Yeah, I used AI to create this thing, and it made so many mistakes. So this one looks the same as this, but they're not. So this one should be 360 orbit, and the coin is rotated 540. What is it? That's 540. So that'd be 720 degrees. So sorry about that. I got where I have to erase some stuff. I got to fill that in. I want to make it look nice. There's another erasure over here I got to fix. Okay, but does that make more sense now? Can we see then that anytime you have an orbit and you have a rotating body going around a center thing that it's orbiting around, like the sun, like the Earth around the sun, you're going to have one extra rotation, which is just the result of the one revolution that it does every year. So instead of 365 days, which we get as solar days, the actual rotations, the days, and you've heard, that a day is actually 23 minutes and 56 minutes long, 23 hours and 56 minutes long, 4 minutes short. But that's just in relation to the stars. So we have to turn that every day, the Earth has to rotate another 4 minutes so that it faces the sun again to complete the day. And you add those 4 minutes up. We just did a rough estimate of 4 minutes because it's slightly less than 4 minutes difference. So it's actually 23 hours, 56 minutes, and so many seconds. But if you add those up, 4 minutes times 360, you get 1,440, which is the number of minutes in a day. So I need to explain this a little bit better, I think, but is that helpful? Is this diagram helpful if I fix it a bit?
Yeah, somewhat help.
Okay. Yeah, and so in trying to explain these things, so I know, I don't want to make things difficult, and I want to take things one step at a time, and I need to even break things down into more steps. But for now, that's what I have is these diagrams, which I think are helpful. So where did the second rotation come from? The first rotation came from rolling the distance of its circumference, just as it did on the flat line. But the second rotation is the inescapable mechanical consequence of traveling in a circle. The act of making a circular orbit literally forces the object to spin one extra time relative to the room around it. If the revolution created an extra rotation, right? That is, and I'm not sure that that's the best way to say it, because the reality is it's the revolution that actually hides the extra rotation. So that's what I'm going to say here. So, well, here it creates the extra rotation in the Earth's maybe I'll say here the Earth's thus we see this in the Earth's parent rotation around its axis, that revolution around the sun hides that. So that should be that. Okay, I don't know how to do this, how to put this in. So the revolution created an extra rotation. Thus, we see that in the Earth's apparent rotation around its axis, which creates the 24-hour day, it is the revolution around the sun that hides around the sun. Okay, adds that hides the Earth's true rotation in relation to the stars. So if you think about it this way, we have the Earth's rotation is actually 365 rotations as we go around the sun. But that rotation, that one of those rotations is lost because of the orbit. Now that seems counterintuitive again when we think about what we did with the coin. With the coin, we find that there is two rotations of the coin. So that would be its true. So we're not, how do I explain it? So I don't want people to be confused. So I got to figure out how not to confuse them. So here we see that there is an extra rotation when you go in a circular orbit from a straight line. But that would be hidden if you were on the coin itself that's revolving. Okay, does that make sense? So if you were on that coin, you would only notice one rotation. You wouldn't notice two rotations in relation to the coin, right? Because you can see there's one rotation of the coin in its orbit. And even though you're rotating, because you're on the coin that's rotating, you're not going to see two rotations of your orbit. You'll only notice one. Does that make sense?
Yes.
Yeah. Yeah. So I still think I need a better illustration because there's some problems with this one. So, the first one is where we're doing one rotation. If we did more rotations, it'd be even more obvious. No matter if you had a smaller coin rotating or revolving around this orbit around a bigger coin, if it took 3 to go around from the perspective of, let me see, if it took 3, that means it would actually, from the perspective of the coin, only go around twice. It would think that it rotated twice. But here, you don't see the light of the coin shining on the planet, rotating. So there's still problems with this illustration. I'm not happy with it.
But
Yeah, William.
have you ever took an actual quarter and tried that on a table?
Yeah, of course.
So you've actually taken a quarter on a table and tried to turn it.
Yeah.
Well, I've been trying to do it and it keeps on, it turns, but
So what you do is you put some graphite on the edge of the coin, put it
well, I
on a
didn't put
piece of
no
paper, and you start it up on heads, and then you roll it. And when it gets to heads again, that line that you draw with that quarter as you roll it will be the circumference of the quarter, right? Because you'll have matched the edge of that. That's why I have that black dot there, right? So you can see the black dot.
Yeah, I see it.
Yeah. And I don't like the way it put the arrows and stuff. But yeah, so it works that way. And if you take a coin and you put another coin and you just have it roll around the coin, you'll see it actually goes around twice. Like it rotates twice as it goes one revolution. So it's the same distance that it's traveling as far as in relation to its edge, because it is doing one rotation from the perspective of the coin that's revolving, right? So if you were on that, you would just see one rotation in relation to the coin, because you travel just one. But from our perspective from above, we see that it's actually 2 rotations. But the person on the coin that's revolving wouldn't notice 2 rotations, which is the problem. It's really hard for people to visualize this. So I have to break it down into different steps, I still think. Like we can do this and show that it's actually rotated twice, but that's not really, it has to do with whose perspective are we looking at, right? So from the sun, like the sun is going to see, if you were on the sun, standing on the sun, if you could do that and you watch the earth revolve in a year, you would see that it did 366
Well,
rotations.
I just did it and it's 7 inches for full rotation.
For what? For a quarter?
Yeah, for a quarter.
Okay. Yeah, I have here 8, but I'm not sure what size. That's just what AI did when it drew this picture for me. I had to do it. It took a lot of work. It took like an hour and a half to do this picture with AI, because it kept making mistakes, and didn't even make any sense at first. And it would have all the quarters all just, the same, with the head sticking up, didn't turn them upside down or anything. So it's very frustrating, but we'll probably get better
Mine
at it.
keeps on rotating. It keeps on like it keeps on slipping.
Yeah. Do your quarters have a serrated edge on them?
Yeah.
Okay, so they should work. But you can see, if you take that moving coin, the first moving coin, and you just go a quarter of the circumference, it'll turn upside down, right? And then you do it another turn, it'll be upside right again, another quarter turn. And then you go a quarter turn again, it'll be upside down. You go another quarter turn, and it'll be upside right, because you're going around a circle. But there's still more to it. And I have to create like a better story. So this is kind of almost there, but it's not quite exactly. So we had dealt with this. So let's go and just read some of the stuff again. I corrected some of it, but the exact same mechanical paradox governs the Earth as it moves through the heavens. As the Earth revolves around the sun, that immense circular journey creates one hidden rotation, right? Because the Earth is constantly curving along its orbit, simply spinning 360 degrees is not enough to bring it back to high noon. The Earth has to rotate 360 degrees and then spin just a tiny fraction further to catch up to the fact that it has moved forward in its orbit. It takes the Earth about 4 extra minutes every single day to keep the sun in its proper place. We can observe this reality by measuring the heavens in 2 different ways. So the star day, that's the sidereal day. If you measure the Earth's spin by watching a distant unmoving star, the Earth completes one exact rotation of 360 degrees. This is its true rotation, that is in relation to the stars, right? This rotation of the Earth in relation to the stars is measured as 23 hours and 56 minutes. So that's the sidereal day is what? Yeah, so it's going to be 23 hours, 56 minutes, and 4.1 seconds. So that 4.1 seconds is that thing that gives us the extra 5.25 days in a year from the 360, right? Because there's 360 degrees, right? So anyway, 23 hours, 56 minutes, and 4.1 seconds. So it's 3 minutes and 55.9 seconds. Anyway, I'm not going to go into the detail of that so much. I don't think, even though I like detail, it can get people to glaze their eyes over. So then the sun, the solar day, because the Earth is revolving around the central fire of the sun, each time it rotates to once again face the sun, that is noon, it has to rotate slightly more than 360 degrees for the sun. This means that the solar day is slightly longer than the sidereal day by about 4 minutes, making the solar day exactly 24 hours. So 4 minutes times 360 equals 1,440 minutes. That's the number of minutes in 24 hours, one full day. So so here we call it, I call it the lost rotation, now the hidden rotation, and I need to make that really, really clear. So Kelly has a thing there about the Canadian quarter. The number of serrations, also known as the reeds or grooves on the edge of the coins, varies significantly between denominations in both Canada and the USA. US coins, modern circulation, dime. 10 cents has 118 reeds, and the quarter 119 reeds. Canadians are 120 to 140. Yeah, the toonie and the loonie are smooth-edged coins. The loonie being the $1 coin and the toonie being the $2 coin. Okay, so a little bit of trivia there. So we have this.
If I may.
Yep.
So the thing that came to mind about those two differences, one reason William might be having a harder time spinning the coin is the edge of the Canadian coin is smoother, so it would spin easier. Does that make sense?
No, it would be easier with an American quarter.
I don't know about that. Okay, whatever. I think it would be harder.
And the U.S. quarter's got them rigid edge. It creates um it creates a I can't think of it. I'm sorry.
Like like a like a place that it catches or drags because it's wider.
Yeah, it creates it's like a tire if it ain't got no threads on it, and if it ain't got no thickness in it, it would slip a whole lot easier than if it has a ridges on it.
Okay, so that's what Theodore is basically saying.
Yeah.
The smoother, yeah. Okay, I'll have to think about that guy.
Yeah. Okay. So so we have this knowledge, we don't fully understand it yet. Actually, one of my guitar students, who's a math whiz, I explained it to him and he just was blown away. He just couldn't believe about the sidereal day that it worked like that. He couldn't visualize it. Now, this thing dealing with the 360-day year, I'm just going to show you. So I had I did some
No, I'm
calculations
sorry,
for
Theodore. More of a traction.
traction. Okay.
Yeah.
Now, okay, so I asked AI about the math, and so this I'm going to have to write a chapter on because we've went back in the past a long time ago before I knew anything. I still don't know anything, but there was this idea that during the flood was when the calendar changed from a 360-day year and a 30-day month to its present, measurements. But one of the problems with that, of course, is that God set up the clock at the beginning, right? So the idea that he would change his clock during the flood doesn't really make sense. But also there is a problem because if we were one is you couldn't actually have a 360-day year and a 30-day month because in our solar system we have resonance, that is, planets are affected by other planets, and so we have an elliptical orbit. It's not a circular orbit. You'd have to have a perfectly circular orbit, and you couldn't. I can't reverse engineer what we have today with the moon and or the Earth and the sun in the orbit. The Earth, in order to have a 360, because if you understand how orbits work, you can't just have arbitrarily place an orbit. An orbit is related to the gravity and the speed in which an orbiting object is traveling, right? So that is, you have to be going a certain speed to be in an orbit. So if you had a day of 360 days, that would make the Earth a lot closer to the sun. And so I asked it because I tried to do the calculations and I was lost. So if you had to do that, the Earth's orbit would shrink by about 1%. So 1% doesn't seem like much, but when it comes to being closer to the sun by 1%, it would make the Earth a lot hotter. So that would be 1.44 million kilometers closer to the sun in order to have a circular orbit with 360 days. The other thing that would happen is the moon would have to be pushed away in order to make the day slightly longer to have a 30-day month. Well, if you did that, you wouldn't have the tidal locking the way that you have it because it's all going to affect everything else. So I have to figure out a way to write this in some kind of some kind of story to explain the whole visualization of it, and I haven't figured out a way to do that. But the point is, you can't reverse engineer what we have now back to, because if you slow down the length of the day, I guess you would have to that, and that would make the let me see, I always get it wrong. So if I wanted to make with the present orbit, if I wanted to make the year 360 days, I would have to have the Earth rotate faster, right? Because I would have to shorten the number of days, the Earth would have to rotate faster. But if I did that, it would actually make the month shorter because the day would be longer. And so the time for the month would end up being shorter. So there's just the Earth, Moon, Sun system. God made it perfect. Everything that he did was good. It never changed. And so it's kind of in our minds, we could think, oh, he could just do this. But he would have to change like all the laws of the universe. So I think God's plan is actually better. And the fact that it works in such a complex way, you know, the idea of simplicity or complex is actually a complex problem. How do you decide if something is simple or complex? Do you understand what I'm asking about simple? So you can have something like, is a snowflake simple or complex in its design?
It's complex in its design.
It's actually not. It's simple. It's just simply a crystal. So there is now, you could
It
have
has six
yeah,
sides to it, six-sided
yeah,
to it.
yeah. But it's what we would call simple in the sense that there's no complex gears or ratios or anything. It's just a natural crystal. But a watch is complex, and that is, we can expect a snowflake to occur naturally because it's just a simple crystal, and every snowflake pretty much looks different. There are some that it's not really true that no two snowflakes are the same, and it's hard to find two the same, but they are sometimes the same. Um, but it's just a chemical reaction. There's nothing complex about it. But a watch needs a designer. It needs somebody to build that watch. And that's something that's complex. The fact that the universe works in this perfect function, but in a complex way, simple complexity? No, it's complex simplicity. uh, yeah, God's clock, this celestial clock, and the way that it works, it measures human history in a way that interlocks in such complex gears. It's wheels within wheels. That is complexity, right? All of these dates, all of these numbers that we've studied, that's a result of complexity. And it is then a witness to design. Yeah, it's well, it's not just irreducible complexity. It's intelligent design, but it's related, right? There is, I guess we could say it's irreducible in some ways. But you can see how man thinks, oh, if we had a 360-day year and a 30-day month, that would be evidence that God existed, right? You know, if we could create a year with that, if we would think that the regularity or that would be an idea of design, but actually the complexity of it is more an example of design. So
I made a mistake.
okay,
It was meters. He had his head it was
millimeters.
7 millimeters, right?
Okay,
Take to rotate.
or
Therefore,
7 millimeters.
yeah, 7 millimeters.
That's not very big. It's got to be
Well,
more
that's
than.
my ruler. That ruler I got on right here is a wooden ruler.
So that's how long it took to go from upright, roll it, and to go upright again.
Yeah, I put it on when I did it. I put it in 1 millimeter upright.
It'd be 7 centimeters.
Yeah, it's 7 centimeters.
Okay. Okay. So
Centimeter is equal with an inch, right? Close to an inch.
yeah, I don't know.
It's 2.5, 2.5 centimeters in 1 inch. And there's 1,000 millimeter, no, 100 millimeters. Yeah, 1,000 millimeters in a centimeter. Or is it 100? Decimal system. It's all based on tens.
Yeah, where is this? Okay, I'm losing my place where I'm at. Not sure what page I'm on. Boundary of the day. Evening, morning, dark watches. Measurement of morning hours. Midnight boundary. Week, okay, the altered dial. Okay. Think visual watchman, secret of the stars. Yeah, this is the section I worked on. Okay, so after that try as you may, try as you might poem, I added this section. Okay, there's a fundamental frustration built into the very clockwork of the heavens. So we read this paragraph. The gears do not perfectly mesh, having established the base units of the day and the week. We must now confront the great mechanical friction of the sky, the orbit of the moon. The solar year is approximately 365.24 days, while the strict lunar year, 12 complete cycles of the moon, is only 354.37 days. So this creates a gap of roughly 11 days every year. Now, I still have to figure out the best way to present this. So I usually use the Islamic system because they have a lunar year and Ramadan, right? So some people know about Ramadan and it makes sense, but it's just every year it's 11 days earlier than it was the year before. But the God of the Bible established unalterable agricultural constraints. He commanded that the Passover must be observed in the spring, the month of Aviv or Nisan, exactly when the barley is ripe for the wave sheaf offering. The law demands that the feast governed by the moon and the harvest governed by the sun be perfectly synchronized. So we're going to deal there with the lunar solar year. Now, imagine standing upon a high, silent plains of the ancient world, long before the digital glow of a clock or the convenience of a printed calendar. The patriarchs lived in a world where time was a living, breathing light. To men like Abraham, the sky was not merely a canopy, it was a message of time from the hand of the Creator. As the sun dipped beneath the western horizon, marking the birth of a new day, the watchman's gaze remained fixed above the setting sun. He was looking for a specific, fragile sliver of light, the first appearance of the new moon. He was a master of observation. He lived by a natural clock, noting the moon's progress as it moved through the Mazzaroth, the constellation of the stars. Now, I remember when I first started really looking into how the biblical calendar worked, like how they looked at the sighting of the first visible crescent. I wasn't really sure how it worked. And a lot of the books that I read, they didn't really explain it well. Because one is you'll always hear that they go out, and look for it near the end of the month. And then if they don't see it, they go out and look the next day. But that makes no sense because the month can only have 30 days. So if you go out on the 29th and you don't see it, then the next day is the 30th, but you don't need to go out on the 30th ever to go look for the new moon. You'd only ever have to look for it on the 29th. right? Because if it's the 30th, you already know the next day is the 1st. And this is really obscured in the literature. It's like people never think these things through. They just assume. But yeah, so only on the 29th. And so you got your little bone calendar there with that 30 holes in it. When it's in hole number 29, that evening you go to look and see, there's the new moon. So tomorrow's the 1st. But if you don't see it, well, tomorrow's the 30th, and the next day after that's going to be the 1st. So, so I still need to kind of expand this a little bit. As the ancients tracked the moon night after night, they noticed a peculiar phenomenon. And this is really interesting, I think. This is not working. The moon completes its true journey through the stars in roughly 27.32 days. If the watchman noted the moon standing next to a bright star on the first night, he would see it return to the exact same star just over 27 days later. This is the sidereal month, the moon's star measure. So we have the synodic month when we see the phases of the moon, but the ancients also observed the moon's movement through the stars. And so they noted that it was 27.3 days that the moon would take to come back to the same point in the sky, right, within the ecliptic. And so that idea of the sidereal month, that is the star month, was understood in the ancient world. And we have records of it back 500 BC, and it was probably known long before that. It's just we don't have records, right? So they noted this, the Babylonians did, in their observations of the sky. They noticed, if there's going to be a lunar eclipse, they knew the lunar eclipse cycle. They also are going to observe the precession of the equinoxes, which we will get into. And these become extremely interesting as we start to put these pieces together in Bible prophecy. So, so again, how I'm going to present this, like this stuff needs to be all rewritten. But this is what I have so far. So, however, a profound frustration arises for the earthly observer. Even though the moon has finished its circle through the stars, it has not yet returned to its new moon phase, because the earth has been moving on its own grand circuit around the sun during those 27 days. The geometry has shifted. The moon finds itself in a celestial drift. It has finished its rotation through the heavens, but it is no longer lined up with the sun. To reach the moment of conjunction, that is to be born again as a new moon, that's actually the word molad. So the molad, which we'll look at, it must chase the sun for an additional 2.25 days, right? So to get that 29.53 synodic month. So you take the 27.3 and then you add 3.2. So that's almost exactly, let me see here. So you got 29.53. It's going to be slightly more than that, but not much. Minus 27.32. So it's 2.21 days from when you have the moon come into the same place with in relation to the stars. Okay, so the sidereal month is the number of times that now the problem that we have here is that this isn't about, well, the moon does it, we don't see it rotating, right? So, so this is going to cause Stephen to lose the will to live again. So we don't see the moon rotating. From the perspective of the Earth, we just see the same face. But the moon is rotating on its axis, right? In relation to the stars and in relation to the sun. Because if it wasn't rotating on its axis in relation to the sun, then it would always have the same side facing the sun, right? And it doesn't. So you understand what I'm saying? So so it's not, but in relation to the Earth, it's not rotating on its axis. Now, the thing that's interesting about this, because I started thinking about it and looking at the sidereal month, that it actually becomes really obvious that the Earth is revolving around the sun from the perspective of the sun. Now, we could argue that the Earth is the center. That is, everything revolves around the Earth from the Earth's perspective. That is, we could describe the sky from the Earth's perspective. Is that wrong? If we say that the sun rises and sets, is that wrong?
It isn't.
It's fine. It's based on relativity. We can just assume that the Earth, everything revolves around the Earth, because they do. Not mechanically so, but they do from the perspective of what we see. But we can't.
Yeah. I was going to say that exact thing. It's basically in relation to our perspective. So it is rising or setting.
So So when people say that it's wrong to say that that the Earth, that the sun rises and sets, and that the Earth actually rotates around the sun, it depends on your perspective, right? Because if we were to zoom out, fly up into space and look at the Earth and the sun and the moon and watch them over a long period of time, and the planets, we would realize that they're actually all traveling very, very fast together through space. So it's, it depends on your perspective. So it's not like there's a right or a wrong perspective. There's just whatever perspective you have. If you're on the sun, it's going to be pretty obvious that the Earth and the moon are, well, you would of course not be alive, but if you could, you would see them moving in an orbit around the sun, right? If you were on one side of the sun, you would see them disappear, and then you would see them come up again, 6 months later on the other side, right? So you'd get an Earthrise from the sun. So there's nothing wrong with any of these perspectives. But also, I do believe that the Bible writers understood this. I don't think that people did not understand that the Earth and the moon traveled around the sun. But they don't describe it in that way, just as we don't describe it in that way, right? We talk about the sun rising and setting. We look at the universe from our perspective. Okay. The 2 gears of time. This extra catch-up period is what creates the 29.53 days synodic month, the month of the phases we actually see from the ground. The star measure, sidereal, 27.32 days. This is the true rotation, in quotations, just in relationship to the solar system or to the stars, linked to a 23-hour, 56-minute sidereal day. Now, so we can see this period of time, 27.32 days. And I need to have a calculation in there somewhere. But if I take 27.32, as I noted before, that there's actually a whole extra month, that means there's 13 sidereal months, the 13 times that the moon travels around the Earth and we can actually observe this, right? That is, the phases of the moon have to do with what the moon looks like, but the moon actually travels around the Earth 13 times in a year, not 12 times. Right? And that should be obvious to us. But we usually just think about the phases of the moon, not its actual amount of times that it orbits the Earth. But but it's actually 13 times that it orbits the Earth. Right? It doesn't really orbit the Earth. We travel together. So, but you understand what I'm saying. So this 27.23 times 13 gives a year of 353.99 days. So it's actually 354. So that is the number of days in 13 months, right? Which, if you have a lunar month, that is the number 12 months, it's 354.367 days. So there's still some time there that we would have to look at. Let me see. Yes. Oh, I did it wrong. Never mind. That was wrong. It's 27.32. I did math wrong. Times 13. Yeah. So it should be the same. No, it's 355.16. Okay. So I did that wrong. 355.16 is the 13 sidereal months. So you can see this. I have to figure out a way to make this interesting and keep the readers, because I can't talk to the reader like I'm talking to you, right? And help you through it. I have to write this in a way that the reader is going to understand each of the steps. And at this point, I'm not succeeding. Like I've really struggled with this. So
Well, we could go over it again and again and again until we get it.
yeah, but I want to write it in the book so that the person can get it right from the first thing they're reading, that they're led on step by step. So you can see here the way that I'm presenting it, it's too much information, right? Too much it's too much like a textbook, a school textbook. And I have to figure out a way to slow the pace of it.
Well, I'm still on the quarter, so I don't know. But the quarter is 1 inch, 1 inch in size, right?
Okay.
And centimeters is 2 inches and a half,
2.5 centimeters.
2.5 centimeters, yeah.
2.5. Okay.
So
Okay. Anyway, for the
rotates twice in
Yeah.
7 inches.
Yeah. And then, yeah. So rotates twice
In 7 inches.
Okay, because so what you're doing is you're measuring the quarter across and you're saying it's 1 inch, right?
Yeah, but I'm rotating it on that ruler, trying to rotate it on the ruler, and it comes
Yeah.
to 7 inches.
Yeah. So what you're doing is you're taking um so let's say your okay, so 3.14. Yeah, I have to figure that math out because what you do is you have to figure out the circumference of the quarter, not the. So if you know the radius of the quarter, you can figure out using pi, right? Pi times the radius squared or something will give you the. But you're saying it's 7 inches to go twice.
Go twice, that's right.
Yeah, and so that it would be 3.5 inches to go once.
Right.
Yeah, But if you were going in a circle, it would go twice in 3.5 inches.
No,
Yeah,
if I was rotating it twice, it would go 7 inches.
right. But if you went in a circle, you only have to it'll rotate twice in 3.5 inches.
Okay. All
Okay,
right.
so let's look at that, because I mean, to me, this is important that people understand it without, you know, ending up in the psych ward or something.
You have when it rotates, it goes on it. It goes. The head goes to the
Can you see the screen here?
Yeah.
So if you take your quarter and you have the head facing up, like upright,
Right.
and you roll it so that it comes around again to being upright, you say it travels 3.5 inches. Correct?
Right.
So because you did it twice, it went 7 inches.
Right.
Okay. So if you put two quarters together, like the diagram here, and you rotate that coin around the other coin, when you've gone a quarter of the way around the coin, it will be upside down. And then you go another quarter of the way, it will be upside right. So
Right.
it will have traveled only half the distance. That would be not even, that would be like 1.25 inches. And then, or 1 and
I see what. Okay.
1.75 inches, right? Then you go around again. So it goes around twice in 3.5 inches of travel, right? Its edge will have traveled 3.5 inches. So that's the idea there.
Okay.
Okay, so but I still need to make this simpler, right? That's the thing that's become really clear to me as I'm working on this book. Now I have a natural tendency to add a lot of detail, and there's nothing wrong with adding detail if I add it at the right time and the right measure. But they have to understand a point. If I explain a point incompletely, or they're not fully understanding it, and then I add on to that, well, they're lost, right? So this has to be like the simplest book ever to read, not language wise, because I'm using, Victorian English and syntax, and I'm using, poetic language and so forth. And I tried, like, I sort of not happy with some of the writing in it. It just seems a little overdone. So I have to figure out, I have to make things simpler, some of the language simpler too. But the illustrations need to be really clear. So, but yeah, I really want this book to work, and I think it can work. I do have other people reading it, who aren't Adventists, and it'll be interesting to see if they actually can get through, the introduction or the first chapter. I'll see what happens, but yeah, you can see there's promise for this book, but it is a lot of work, and I get bogged down. I keep going down rabbit holes all the time when I'm writing. I just look into things way too in depth, but that's kind of my nature. So, any final thoughts about this? Any inputs or suggestions?
And just keep doing it slowly.
Okay, well, thanks. So
Slow,
you're
slow,
enjoying it.
slow as we possibly can. Yeah.
Yeah. Okay. yeah, I really have to like, because I gotta set, like, to get into the biblical calendar, into the moad, I can't jump into that right away. I have to get the person understanding so that they're familiar with what we're doing, how the sky works. See, it's just that people nowadays don't really pay attention to the sky because of all the light pollution. So there's lots of things we don't notice, and lots of things I didn't even notice until I started studying, the biblical calendar, and like, oh, like even just the idea of how they figured it out. Like, I wasn't sure, like, did they figure it out at in the morning for, how did they figure out the equinox? You know, all these types of things. We're just not used to doing that. Okay. Anybody else? Stephen, did you have a comment?
Just noticing the
reference sort of connection to the Levites with the number 27.3.
Yes, the 273. I'm going to have a section on that. Because there's a whole bunch of relationships between the sun and the earth and the moon and the triangles, like the orbits, the distances and sizes that all relate to 273. So it's a number that exists in nature. So the gestation period of man, it is the absolute zero. If you have, freezing as being zero, and you have boiling as being 100, then naturally absolute zero is 273, minus 273. So, yeah, Jeff, you have a comment?
Oh, no, I didn't say nothing.
Yeah, so there's a whole bunch of things in, because I'm planting all of these seeds. So, like the 273, I want people to remember that number because we're going to deal with it in the prophetic part of the book, right? So this isn't going to be like a small book. This is going to be quite a comprehensive book. So that the introductory part, dealing with the celestial mechanics, it might end up just being this part of the book called, God's celestial clock, maybe like the first section. And in the second section is going to be dealing with all the calendars. And then the third section is going to be dealing with prophecy. So I keep rearranging all of the material, which is not the best way to write, but that's how I tend to write. Is I tend to like try to write a book from the beginning to end, but then you keep wanting to add stuff, and then like I don't have it organized yet in my head exactly. I'm getting there, but it's just I see the problems that I'm running into, and I have to figure out how to solve them. Okay, so let's close with prayer. Dear Father in heaven, thank you again for the time that we have had to study your word. And even though we haven't really read too many scriptures, we have looked at the sky and how you have created things. And we are thankful, Lord, that you have made the sun and the moon and the stars to keep track of time, that they measure our lives, they measure prophecy. And we know, Lord, that you have a purpose in all these things. So help us to understand them, and may this Sabbath truly be a blessing to each one. In Jesus' name we pray. Amen.
Amen. Amen. See you all tomorrow.